The lack of common grounding and bonding between buildings and their services poses several safety hazards. In the event of a fault, current can flow through unintended paths, increasing the risk of electrical shock or fire. When an electrical fault occurs in one building, it can cause the ground potential of that building to rise significantly. If the other building is not properly grounded and bonded, equipment or personnel in that building may be exposed to dangerously high ground voltages. Separate services in the absence of common grounding can create electrical hazards for workers or occupants working in both buildings. To mitigate these safety concerns, the following steps should be taken. Firstly, establish a common grounding system that connects all electrical systems in both buildings. This will ensure that all equipment and personnel are protected from the effects of electrical faults. Secondly, bond the electrical services of the separate buildings together to ensure that they share a common ground reference. Thirdly, install transient voltage surge suppressors, TVSSs, at the point of common connection to suppress voltage spikes and transients that may be introduced by the separate services. Fourthly, review and update electrical drawings to reflect the changes made to the grounding and bonding systems. It is important to ensure that the emergency generator is properly sized and installed to handle the electrical loads of both buildings. Regular maintenance and testing of the grounding and bonding systems should be performed to ensure their continued effectiveness. All work should be performed by a qualified electrician and in accordance with the applicable electrical codes and standards. Grounding and bonding are critical for electrical safety, ensuring a low impedance path for fault currents to return to the source, thus facilitating the quick operation of overcurrent protective devices like circuit breakers or fuses. Without proper grounding and bonding, fault currents may find unintended paths through people or equipment, creating dangerous shock hazards. The ground potential rise (GPR) phenomenon occurs when a high fault current flows through the grounding system, causing the voltage potential of the ground to increase relative to remote earth. This can be hazardous if there are differences in ground potential between interconnected systems or buildings. To address this, a common grounding electrode system should be established, connecting the grounding systems of all buildings and services. This system typically includes a grounding electrode conductor, which is connected to a grounding electrode, such as a ground rod, ground plate, or underground metallic water pipe. Bonding involves connecting non-current carrying metallic parts of electrical equipment and systems together to create an electrically conductive path. This path helps to equalize the voltage potential between these parts, reducing the risk of electric shock. Bonding conductors, often made of copper or aluminum, are used to connect metal enclosures, conduit, and equipment grounding terminals. The size of the grounding and bonding conductors must be appropriately selected based on the size of the service entrance conductors or the overcurrent protective devices, in accordance with the National Electrical Code, NEC tables. For example, NEC Table 250.102 C1 provides guidance on sizing the grounding electrode conductor for grounded systems. Similarly, NEC Table 250.122 specifies the minimum size of equipment grounding conductors. Transient voltage surge suppressors, TVSSs, are devices designed to protect electrical equipment from voltage spikes and transients caused by lightning switching surges or other disturbances. TVSSs divert the excess voltage to ground, preventing it from damaging sensitive electronic components. They are typically installed at the service entrance or at the point of common connection between different electrical systems. When separate services are interconnected through a common emergency generator, TVSSs can help to mitigate voltage transients that may arise from the different characteristics of the services. Regular maintenance and testing of grounding and bonding systems are essential to ensure their continued effectiveness. Visual inspection should be conducted to check for corrosion, loose connections, or damage to grounding and bonding conductors. Ground impedance testing can be performed to measure the resistance of the grounding system and verify that it meets the required standards. Additionally, continuity testing can be used to verify the integrity of bonding connections. All electrical work should be performed by a qualified electrician who is familiar with the applicable electrical codes and standards. The NEC provides comprehensive requirements for grounding and bonding, and it is important to adhere to these requirements to ensure electrical safety. Local codes and regulations may also have additional requirements that must be followed. When installing an emergency generator to serve multiple buildings, it is crucial to ensure that the generator is properly sized to handle the combined electrical loads of all the buildings. The generator should have sufficient capacity to supply power to essential loads such as lighting, life safety systems, and critical equipment. Load calculations should be performed in accordance with NEC Article 220 to determine the total electrical load of the buildings. The generator should also be equipped with appropriate transfer switches to automatically switch between the normal power source and the generator during a power outage. These transfer switches should be properly sized and installed to ensure a seamless transition of power. In addition to grounding, bonding, and surge protection, it is important to address other potential safety concerns related to the interconnected electrical systems. For example, if the buildings have different voltage levels, such as 120/240 volts and 277/480 volts, it is important to ensure that equipment and wiring are properly rated for the voltage levels to which they are connected. Step-up or step-down transformers may be necessary to match the voltage levels between the buildings. Furthermore, it is important to coordinate the overcurrent protective devices, such as circuit breakers and fuses, to ensure that they provide adequate protection for the electrical systems. Selective coordination studies should be conducted to determine the appropriate settings for the overcurrent protective devices to minimize the extent of any power outages during a fault condition. Electrical drawings should be updated to accurately reflect the changes made to the grounding, bonding, and electrical distribution systems. The drawing should show the location of all grounding electrodes, bonding conductors, TVSSs, transformers, and overcurrent protective devices. The drawings should also indicate the voltage levels, conductor sizes, and equipment ratings. Accurate and up-to-date electrical drawings are essential for troubleshooting, maintenance, and future modifications to the electrical systems. In summary, when separate buildings with their own electrical services are connected by a common emergency generator, it is crucial to address potential safety concerns related to grounding, bonding, surge protection, and voltage coordination. By establishing a common grounding system, bonding the services, installing TVSSs, and updating electrical drawings, it is possible to mitigate the risks and ensure electrical safety for workers and occupants in both buildings. It's important to ensure compliance with the National Electrical Code and other applicable standards for electrical installations, especially when dealing with multiple buildings and shared emergency power systems. Let's consider the specific implications of not having a common grounding and bonding system. Without it, a ground fault in one building could energize the metal enclosures of equipment in the second building, creating a shock hazard for anyone who comes into contact with them. The path of the fault current would not be well defined, and it could flow through unintended paths such as water pipes or structural steel, increasing the risk of fire. The ground potential rise in one building could also affect sensitive electronic equipment in the second building, causing it to malfunction or be damaged. The separate grounding systems may also have different reference points, which could lead to circulating currents between the buildings. These circulating currents can cause overheating of conductors and equipment, as well as interference with electronic systems. Furthermore, the absence of a common grounding system can make it difficult to troubleshoot electrical problems and can increase the risk of misdiagnosis and improper repairs. The electrical systems in both buildings should be treated as a single interconnected system with a common grounding and bonding infrastructure. This requires careful planning and coordination to ensure that all the necessary connections are made and that the system is properly installed and maintained. The grounding electrode system should be designed to provide a low impedance path to ground for fault currents. This may involve installing multiple ground rods or plates or connecting to an underground metallic water pipe. The bonding conductors should be sized according to the NEC tables to ensure that they can safely carry the maximum available fault current. The TVSSs should be selected based on the voltage level and surge current capacity required for the application. They should be installed as close as possible to the equipment they are protecting to minimize the effects of surge impedance. The overcurrent protective devices should be coordinated to ensure that they trip in a timely manner to clear faults and prevent damage to equipment. This requires careful analysis of the electrical system and the selection of appropriate settings for the circuit breakers and fuses. The electrical drawing should be reviewed and updated to reflect any changes made to the electrical system. This includes adding new equipment, modifying existing circuits, and relocating grounding and bonding connections. The drawing should be kept in a safe and accessible location for future reference. Regular inspections and testing of the electrical system should be performed to identify any potential problems and ensure that the system is operating safely and reliably. This includes visual inspections of grounding and bonding connections, ground impedance testing, and insulation resistance testing. Any problems that are identified should be promptly corrected by a qualified electrician. In addition to the technical aspects of grounding and bonding, it is also important to consider the human factors involved. Workers and occupants should be trained on the importance of electrical safety and the potential hazards associated with electricity. They should be instructed on how to identify and report electrical problems, and they should be provided with the necessary personal protective equipment, PPE, such as insulated gloves and shoes. Warning signs should be posted in areas where there is a risk of electric shock, and access to electrical equipment should be restricted to authorized personnel only. By addressing both the technical and human factors, it is possible to create a safe and reliable electrical system that protects workers, occupants, and equipment from the hazards of electricity.